You've actually seen a number of examples already from some of the speakers, but United Technologies, we're about half aerospace, so we do a lot of PHM applications on jet engines and other control and large aerospace systems. We also do quite a bit of work in the area of buildings, so we have many different building systems, right? The elevators, the HVAC, the security systems, access control, and then another kind of small assortment. But in terms of PHM, much of our work these days is in what we call the aftermarket, which is really how do we maintain the health, how do we service these, how do we collect data from the field, and really reduce the amount of repetitive tasks and simple tasks to make the maintainers of these systems more efficient.
Thank you. Dr. Margineantu.
Hi. Thank you so much for the introduction. So in Boeing, I sit in Boeing Research and Technology, and Boeing has two big business divisions, commercial airplanes and defense. In PHM, we do support both businesses and the platforms that are developed by them, so commercial airplanes as well as on the defense side. But we are also looking at health management in the manufacturing arena. So our manufacturing process is extremely complex. It can be optimized, and right now, as everybody knows, if you order a 787 airplane, you'll get it in 2024. And so we want to speed up and to optimize these processes. Now, in research, there are these obvious questions, and we've seen here talks in mostly supervised learning. And I've worked most of my life, probably 80% in supervised learning, but I wanted to raise the attention towards our thinking in going beyond this. We have this hammer, and it can solve some problems, but it has inherent limitations. And so we tried to think about basically building intelligent systems for decision making, and I'm going to talk later a little bit about that. So that's where we're going in our thinking and in our research.
Thank you.
Thanks, Abhishek, for introducing me. So in the GE Global Research, in GE overall right now, we are driving the initiative called Industrial Internet. So here it is not, it is basically Internet of Thing, you all are hearing about that. So, but it is Industrial Internet of Thing, essentially to deal with these large, very big assets like aircraft engines or oil wells, refineries, or whatever you name. So yeah, GE is playing into almost every single area what you touch your life, basically from healthcare. We have MRI scanner, CT scanner, ultrasound, plus aviation. We have jet engines. We service them or manufacture them. Then we have all the 30%, more than 30% of the power of the world is generated by equipment supplied by GE, from the wind to coal plant, or it is gas-based power plant. So we are monitoring right now around 300,000 plus equipment. All that data comes to our cloud, essentially. And we have over $200 billion services backlog in these equipment which we have sold. So I think our main goal is to improve the productivity, services productivity. Essentially, we have been doing it since last 15, 20 years to collect this data and to reduce our cost to operate these contracts, as well as retain those contracts, provide some more higher revenue to our customers. So that's why we have been using machine learning, physics-based approaches, hybrid approaches extensively in all these areas, basically. Now, whatever we have done in last 15, 20 years, now we want to take it to the outside world and basically make it available in the form of the platform which we are building called Predicts platform. And then brain of that platform, I will say, is a digital twin framework, which is the per asset model. We say this is continuously learning. I will talk more details, and if you have any more interest, we can talk later also after the talk. yeah, so a lot of exciting initiatives are currently going on.
Thank you, Achalesh. Any questions from the audience? I have a really long list, so I can go on. Achalesh, you mentioned about digital twin. Can you talk a little bit more about what it is and any other big bets GE is making in this area of applying machine learning to the data sets that are being generated from the assets GE has?
Sure. Yeah, so digital twin concept, I will say it is not very new, but the way we are approaching it, it is entirely in different manner. So think about the Amazon or Google, all these companies who are the leaders in their own area. That's what I'm speaking their name. And so they are collecting a lot of data. And who's generating this data? They are not generating this data. This data is being generated by the users. And so let's take the example of the Amazon. So they started initially with the segmentation, like they take the complete big population, and then they are building some of the models to do the market segmentation, like the age or gender, those kind of things. And then after that, they started collecting the information about every single click, what reviews you are writing, what reviews you are reading, and then they started building the model of one. Like think about the fleet level model to the model of one. After they build the model, then now they are trying to monetize that model. And that model is essentially you are predicting, this is, if you like this book, you may probably like this other product also. So that is your P&L of one. So going from your fleet information to model of one to P&L of one. And similar thing is applicable to our industrial assets also. Like we have, if you think about 10 years back, what we used to do? We used to do some fleet segmentation. We used to build some of these survival analysis curve or viables and other things based upon hours, starts, all those kind of information that is basically at the fleet level where there are hundreds or thousands of these assets are. But now you can track every single, because of this big data, you are collecting a lot of information. You can look into every single flight. You can also know that, okay, this engine has flown through Middle East where there is fine sand, and that sands caused this problem to your part. So you are going from fleet level to individual part level. So that is becoming model of one. And now you take that model and you are predicting it for your predictive maintenance, or you are doing it for the optimization. And now you are becoming P&L of one. So that's the philosophy we have. And we believe that there will be millions of the digital twin models, because every single asset, there are multiple failure modes, there are multiple outcomes, and you are building these models to achieve some outcomes, specific outcomes, and then you have to manage these models, continuously learn these models. So that's what we are in this journey, basically.
Thank you. Dragos, so you mentioned that Boeing is making an investment or looking at manufacturing in this area of PHM. So in that light, or even more, what do you think are the big bets coming from Boeing in this area?
So I want to talk a little bit about the research question. So these systems that we try to monitor the health, to predict failures, etc. We rarely think of them as, so we throw at it standard, modified, adapted, supervised learning methods that do not take into account the state of these systems at all. We hack them into some features. We solve some prediction problems. Yeah, for some failures, we have solutions. We have published. Many people have published. But think of the scale of the number of these predictions. We have millions of these. We can't move towards these millions by hacking in solutions like these, no matter how big our organizations are. So I'd like to invite everybody, we're thinking internally and we're building towards this, to think about a disruption here, and about state-based models, and about technology that comes in from AI, like planning, in which we think about a goal, we think about a goal state, like reinforcement learning. And I know it's hard. I know it's a totally different mindset. But these are the kind of things, the kind of models that would scale. One problem is that we all have here. We do these predictions. We predict that this engine will fail. We do predict that okay, this airplane will be late. But we never take into account, for example, the effect of that decision, the corrective action that is typically taken. This problem, we have it in our systems, and healthcare has it, right? It's very hard to hack that into all these supervised learning methods, no matter how we do it. We can hack them into 1 solution, 2 solutions, 10 solutions, 100 solutions, but it won't scale. We have now the computational power to think about markov decision processes, to think about goal-driven actions in which we take sequences of action, rather than predicting, okay, this engine will fail, I predicted, I have an ROC curve that predicts that. How about predicting the sequence of actions that will lead to a minimum cost of operation of an airplane or an engine and so on? So that's one line of thinking. The other one, which is closer by, is also to think about our machine learning solutions as being embedded into the systems that we develop. And we had a AAA symposium on embedded machine learning, but what is this about? The machine learning solution rarely has to do a classification problem. It typically is an advisory system to a human, or an advisory system to an advisory system, or it plugs into something else. Now, experiments that we've done and others, and there is also an interesting book about this, Our Robots Ourselves, just look it up on Amazon, show that if we think a little bit, let's all think about our favorite machine learning algorithm and think of what is it feeding its output into. It's some sort of an engineer, expert, or another classification system. And let's try to optimize that output, not in terms of classification, but in terms of the output of a classifier. My deep belief is it shouldn't be a class. It should be a higher dimensional feature vector, very much like in deep learning, something, but a subset of the layers there, in which we input whatever that engineer needs to. It's been proven, for example, in this book, it's shown that pilots are notoriously in bad weather much worse than automated pilots. Automated pilots can, the automatic pilot on our airplanes can land in 0 visibility. Well, they engineered automated pilots to provide the feedback that the pilots need. Well, we produced that way superhumans that make actually even better decisions than the automated pilots. That's the kind of thinking that we'd like to have. So everybody who's working here on PHM and so on, think about the system, the embedded system that you produce your learner for, and try to optimize your output for that system. And think, in the simplest case, if you're from the academia, take your output and be a classifier that you trained and it's fixed. And try to learn those features. And the deep learning people here will find that very easy. Those are the kind of solutions that we have to move into. Our systems will be humans and computers and machine learners that are very powerful in making these decisions. So,
thank you. Yeah, so Michael, it's pretty much the same question to you too. UTRC is sort of a very diverse organization having so many different business units. I'm sure both as a business and as from the research point of view, you're making some big bets. Can you talk about that?
Sure. First of all, I agree with what both of these gentlemen said. And Dragos, I can thank you for kind of the lead in to what I think is kind of one of the big bets for us, which is, and you saw some of the precursors again in some of the discussions where we're looking at analyzing physiological information from humans, whether that's EEGs, heart rates, and other things. But the end game for all of this is when we're building our PHM systems, our diagnostic systems, keeping in mind that the end user is a human. What we would actually like to be able to do to close the loop while we're actually training these systems is to monitor the effect on the person, right? Whether we're providing them the correct information or not, being able to detect that in real time, and in the training of these models to actually influence the fitness, so to speak, not only by the classical fitness, that our machine learning algorithms currently use, but also by the response of the human to the information you've provided them, right? And so we see this, in one sense as being a way of having our models converge to more quickly, right, to better solutions and more effective solutions, right? And again, we realize that we're at the very nascent stages of this, right? This will be work that'll be done over the next, we'll say 1 to 3 years, where we're really able to make significant progress, but is really just the first step around optimizing the total human-machine system.
Thank you. Are there any questions in the audience?
Hi, I have a question for Dragos. Especially for goal-driven methods, let's say Markov decision process, or if you want to go one step forward, like any reinforcement learning kind of system. One of the biggest challenges in learning part, you need a lot of sequential data, and actually the people who make the decision and those decisions in the process. And any reinforcement learner, you need proper initial conditioning, and then learning the whole system in all the state spaces possible, at least few of them. So what is how do we want to address that challenge in real field, or whether you want to learn it on the background in the real, so when the real system is running. So what is the, yeah.
Thank you so much for the question. I don't think I have a full answer, but in the previous talks, I heard here in the audience people asking, do you have the data? Can you make the data available? Let's move beyond that. We don't need a data set. We need, and we are not doing it here, some simulators that are well abstracted. I can't simulate my entire factory. I can't simulate my entire airplane. But people in simulation technology, and think, for example, Facebook has efforts in this direction exactly because they have this thinking. We have to think in that direction, and there is no effort. And no effort, at least, you correct me, if you have these efforts, God bless you. But if we had these simulators, even for subsystems, and I'll give you one example. I was part of DARPA's Bootstrap Learning. In Bootstrap Learning, we had access to a simulator of a subsystem of the International Space Station. And we had to optimize, we had to learn a certain thing on, decisions on, it was a PHM question doing machine learning. If we had that kind of simulator, and that was made available by, I think, BAE or one of the other subcontractors. It was very useful, much more useful than having access to some data. We all struggle for data, and yes, we'll work on data, and this data is extremely biased, and it comes, if I give you the data, I have to have 2 days of telecoms to tell you what's in the data and so on. How about we work, this industry, in order to leverage as much as possible, what's outside, we need to have these kind of simulators of, and yes, the states in these simulators will be a well-thought abstraction, but if I send you the simulator, I know that you if you're smart in the academia, I know you're not in the academia, but in the academia, I can use your solution. So it's that kind of thinking. No, I won't be able to make available the data, and I don't think that data will be useful no matter how much and how big it is in the general case. And I don't think also that I have fully answered your question. By simulating that subsystem of the International Space Station, obviously there are things, that's part of, a bigger system, but that's the place to start. Let's think about that, because that will make us also more attractive to, and also the problems that we have, for example, anomaly detection, we'll be able to nail it down. It's not, the anomalies that we have to deal with in PHM are extremely complex, and they are conditioned on some sort of prior knowledge. If that's captured in some of these simulations, I think the academic world could work on those, and it's all a win-win. I don't think we have many simulations people here. Here, data mining and machine learning, but we should team up. We have a team doing simulations, and I'm trying to push them in that direction. And I know that Facebook has built up a big simulation effort together with their machine learning to do exactly these kind of things for the kind of decisions that they care about.
So simulations are wonderful. They assume you know what is going on in the system. That if it's a very complex system, as you also alluded to, it becomes more difficult. So I was wondering whether you've thought of using, say, causal models, which are sort of causal. You just not a machine learning model necessarily, but a causal model which understands the sort of Bayesian causal models or structural models, where then you can sort of use it like a simulator.
That's actually a first step moving forward, and we are looking at least one particular area in final assembly in which we do this kind of modeling. That would be a first step in building that. I agree. If we have a full simulator of the entire thing, we won't need machine learning and data mining. But abstracting through probabilistic models, causal models, trying also to use machine learning, using machine learning. Last year's invited talk by Susan Athy touched upon learning causal dependencies, from observations. I think that's something that we need a little bit more attention, and that would be a first step. I agree. Yeah.
So I really like the point that was made earlier. I think Dragos made it, that machine learning in itself is rarely the end goal, or it's not the system which is taking the decisions or taking any next steps. It's mostly a human or an expert and an engineer who's going to look at the output from a machine learning system and then come up with a solution or an action. Now, the challenge in getting successful machine learning algorithms is that humans, they rarely care about the accuracy of the algorithm. They want interpretability. And I would like to know from your experience and the action that you're taking today, what are some concrete steps or examples of interpretability that you have implemented in your organizations to enable this?
You want to start, and then I guess all of us have good, based on what I know, all of us would
Yeah,
have
actually,
good
if
answers.
all of you can weigh in on that, that is actually a very important question we get asked a lot, that the systems that we are looking at are critical systems. And we heard earlier that a lot of these models also need to be certified. So how do you balance interpretability, prediction accuracy, and the use cases? So if all of you can weigh in on that.
Yeah, I think it totally depends upon what outcome you are trying to achieve. And so let's take the example. I think there were a lot of presentations here on the anomaly detection side. So for example, even if you are using deep learning, you don't understand that, but you are identifying the residuals for individual sensor level. And from that, you can interpret it basically that, okay, this particular signal or feature is causing some problem. It is correlation, not causality, but it needs to be the combination of some domain expert as well as the machine learning combination. And machine learning in itself will not be able to produce good results, which we have seen in the GE basically. Second thing, whenever you are working on the machine learning problem, then first start with sitting with some domain expert and take the example, like there were many examples of combustion. Why the combustion example first came here? Because it is extremely hard to model combustion physics. Nobody has been successful so far. We are modeling, but the modeling is specifically modeling this, the instability in the combustion. We have tried quite a bit in GE. There are very good models, but you can't model everything. There are a lot of uncertainties associated with that. And that's why some of these places, yeah, machine learning kind of the systems can work. So how to bring that, the causation as well as machine learning should be able to explain the things. I think that becomes very, very important question for the, adoption of these kind of the solutions also in the industry. So I think, and the second thing is use as much as physics model as possible. Like how many people know here, like how many sensors are there? We talk about the big data, but how many sensors are there in one engine? Like take the example of G90 engine with G manufacturers. There are only 14 sensors. So you may be thinking there are 500 sensors. No, there are only 14 sensors. And then people will say that why there are 14 sensors? Why can't we instrument it? Because if you put more sensors, it increases the weight of the airplane. If it increases the weight of the airplane, there will be higher fuel consumption. So that's why there is the design optimization. That is one aspect of that. And second aspect of that is essentially the robustness of these sensors, because these are for heavy duty applications. The plane is flying from one corner of the world to the another corner. So that's why the sensor becomes the bottleneck. It will fail and it will cause the problems basically. So that's why it needs to be vetted, all these sensors, very robust testing and other things. And it costs millions of the dollar to put even instrument one sensor. That's why you don't see those so many things in the industrial internet kind of the area for the heavy assets. Taking the subset of the sensors, because all the sensors are not useful, only the few sensors will be useful, and then build the machine learning model based upon that. That brings more confidence to your domain experts, whoever are going to use this. So that's what I think we have learned. And that's what we use the virtual sensor, concept of the virtual sensors. Like I have, just like you mentioned, the simulation model. Like every OEMs, every manufacturer has design models. And that's what we use, the thermodynamic model, to estimate the internal state of these engines or these parts, basically. And then those becomes your virtual sensor. Although you have only 14 sensors, but you can generate 50 additional virtual points from your simulation runs. And those you feed to machine learning models. And then you may be getting much more transparency in the system. And that's the way we operate, basically.
Yeah, so the understandability of models is key. And also I want to point to another aspect which is beyond understandability, actionability. And I'll give you one example with a solution that we have built for airplane health management, in which we were basically making very accurate predictions. Supervised learning, very well engineered features and so on, very accurate. Went there with the domain experts, engineers, and basically they said that the models, and so what we did was we learned complex models, and on top of that we tried to extract rules, all sorts of hacks that kind of state of the art, what we all do. Well, these models didn't make sense. And to make a parallel to a system that we understand, what we were doing is basically like predicting, for example, let's say you fall, you trip, you break your leg. All sorts of things go inside, right? Your blood pressure is high, headaches and so on. You go to a doctor, and the model that he's running, he says, oh, here, take some blood pressure medication because this is your problem. This is what we were doing. And the doctor, a bad doctor does that if he relies on a supervised learner, because we find these features simply because, for example, the circulatory system is correlated to all the subsystems. And you see some features in the circulatory systems that, predict that, if you fix that, you fix your problem. Now, we can do all sorts of hacks, and I recommend all of you to, for example, Rich Caruana's work over the years, and it was published in KDD over the last 3 years, extending the generalized additive models into very powerful, predictive, comprehensible models. He applied them for healthcare systems. And we can do all sorts of things. But if we go back to, for example, state-based models, if we do a planner that will make decisions, those you can extract inherently from them an explanation. In the inverse reinforcement learning work that we did, simply the model itself could explain, and I'm not going to go into details, but the model themselves can be easily used to explain what was the rationale of the decisions. So if we think a little bit different, and reinforcement learning, planning, and so on may provide us inherently more understandability. They are more complex, but they can provide us more understandability.
Just a quick one. You're not going to go in detail. What is the inverse in the inverse?
So in reinforcement learning, we have states and the reward function, and we try to learn the actions. In inverse reinforcement learning, we observe the actions. I observe your actions. You're here, and so on, and you came to this conference, and we try to infer the reward. How did we use that? We used the reward function as the estimated reward function as a basis for decision making. I assume that if you have a good estimate of the reward function, you make principal decisions. So that's what inverse reinforcement learning is.
So in terms of interpretability, I guess we start with kind of the opposite of the usual saying, but is don't take a gun to a knife fight. You should always use your simplest method. You should always we have had our research center's been around over 85 years, so we have more than 85 years of physics-based models and domain experts to rely on. Always use the simplest possible thing that you can. One of the things that we've tried to do with our machine learning, more of our data-driven types of methods, is especially with the deep nets, because they're in many ways kind of input agnostic, along with all of the sensor data or what other type of information you're trying to train with. You're also free to put in any other kind of physics-based model knowledge that you have, right? Whether those are, actual outputs of, the expected outputs of physics-based models, or parameters, or, subsets of observables in the systems. And like we spoke about before, where you can do virtual sensor estimation, right? You can also be doing estimation of the model parameters and the physics-based models themselves. So in a sense, as you're training things, you also get a verification of the physics-based behavior that people are more familiar with, right? And so if you can convince the people who are going to be using the models that what you're saying is corroborated by sensible, physical outcomes, right? Then that also helps make them more interpretable. And then last, on some of the more recent work that we've been involved with, we haven't spoken about it here yet. I think we spoke about usable, but I mean, an enormous thing in terms of getting things implemented is really the trust factor, right? Which is to get anything implemented, especially in a large organization, the people who are going to use it have to trust it and be comfortable using it. And one of the ways that we approach that, especially now, where we're actually doing some modeling. Like attention models are one example of this, where you're trying to learn an expert who's doing a repetitive task, let's just say an inspection task or something like that. They're doing it over and over again. If you can learn how the person does the process, right, have them actually involved in the training of what to pay attention to and what actions they're taking. If the model is trained properly, I mean, by by definition, you're basically explaining that that model was trained off of your expert actions, right? And then it's really just a matter of verification and giving the person time to grow comfortable that the model is actually able to replicate their actions, for them to adopt it, and then to, I mean, usually what we're looking for in these cases, especially for highly repetitive tasks, is the removal of the many trivial tasks so that the inspectors can be used for, right, the more complex decisions that need to be made. So that's really, I would kind of think of those as the 3 steps we've used to help drive interpretability and comfort with the models.
Thank you. There was a question in the back.
I have a loud voice.
Yeah. Okay.
Would you care, in any way you choose to comment on the interaction between machine learning, data science, and critical systems and safety systems? Because that's the kind of terrifying boundary we face.
Sure. So we also face that up until last year, right? We also, aside from the jet engine company, also used to own Sikorsky helicopters. So we're very familiar with the commissioning aspects, right? In terms of trying to get any kind of data-driven system, anything that isn't purely deterministic, commissioned for flight critical, right? Safety critical systems. A couple of the things that we've looked at here are most recently we have people who work on the formal methods side, so they're completely deterministic models, right? And those of us in the machine learning community, all have kind of a bias as to what their limitations may be. But those methods have oftentimes provable bounds, right? Provable performance. So what we're looking at is in many of our machine learning methods, whether we can show that those machine learning methods can be bound by formal methods. And that at least you get to use all of the, we'll say, superior performance of a data-driven model when they are, better. And you also have the formal method to backstop your outputs, right? In terms of, so it gives you that confidence that the model isn't going to run amok when it hits something that it hasn't seen before.
I totally agree that formal methods should be used in those high-risk decisions. Also, there are some hard research questions there. Also, as part of the research community, I'd like us, including myself, when we come and present things, in addition to the ROC curve, to also talk about any aspects of robustness. So this question goes into the robustness of if we deploy it as part of this man-computer system and so on. We should start thinking about measures of robustness and how we do it. And again, with supervised learning, it's hard. With ensembles, it's extremely hard because they are, you don't know what they do inside. I like, typically, for example, when we do learn value functions for reinforcement learning, neural nets tend to have this more smooth output where we can take care of robustness so that you don't take that really bad decision. But we're working very hard with our counterparts in the two businesses in Boeing to address these questions. And I think that the straight question is that right now, correct me if I'm wrong, we don't have an answer. If you ask me for a predictor for a, highly unlikely event, anomaly detector, to be really accurate, we don't have an answer for that. In a parallel workshop, Jeff Schneider was giving this example of, you may all be familiar with their monitoring of over-the-counter sales in Pittsburgh to predict an anthrax attack. the fact that that was an extremely rare event and highly damaging, there was no way they could prove themselves and so on. And then they shifted to try to use the same technology to predict hurricanes, because but I don't think I would trust that just based on their prediction of hurricanes. It was a nice discussion. So we don't have methods to do that, and the way to validate and to prove, I think we should look more at formal methods, and we'll have an invited talk here at KDD by Joe Hellerstein, who I hope will address these kind of questions. We need to bring in knowledge from there.
Yeah, I think, so I have few examples here, like safety critical system. If you are asking about closed loop control, yeah, it is scary right now, basically. But if you are talking about PHM application for your maintenance optimization or your operations optimization side, there are a lot of success stories in GE, basically, where we are extensively using machine learning techniques. Those are in production for maintenance optimization as well as your anomaly detection, for example. There will be some false alarm rate, that's true, but it helps. Like having something rather than having nothing is always useful. And another thing is that you can't model everything through physics because of the variability in the manufacturing, variability in the materials. Like if you see the materials variability, if you see these material curves from the material science, there is plus minus sigma limit. If suppose your life is supposed to be 20,000 cycles or flights of aircraft engine, it can be anywhere between 10,000 to 30,000. It's so much variability is there. And that's why you put the safety margin and you put those things. And whenever we launch any new product, there is definitely some conservatism to that. But as you get more data, you learn from that, you try to push those margin to optimize your maintenance. And there I have personally seen and worked that we have a lot of success stories. In fact, we got the approval from FAA actually when we demonstrated to them. And the way you want to use, like, still you will be using linear regression or some of those things in your final model, but at the step of feature selection or feature extraction, you use a lot of machine learning. That's another thing. So another point I have, like, think about this area is a lot of data issues there in the sense like you have very less amount of the events, otherwise nobody will be flying. And there are very less number of issues associated with that. The things are very, very robust, and that creates the problem. And at the same time, when there is any problem, then these OEMs like GE or Pratt, they will work on, the designers will work and they will fix the issue and the roll out that new solution. So you are not going to see the same problem now again in future, correct? So there are those kind of the issues. So machine learning can help in generating the data. I think let's think from that point of view. How much inspection data we use right now in our machine learning models? Because these inspections are done by humans. So very limited scale, we do the inspection in our shops and other things. But if we have the auto inspection, like similar to whatever UTRC team has shown, so we have also productized some of the auto inspection solution using deep learning in GE, where now with very, very high accuracy, you can get very, very good estimate or the view of your parts. For example, this is the crack, or this is the spallation, this is the thing. So otherwise, earlier there was failed or healthy. We just get the binary labels. Now you can get the quantified labels also. So machine learning is helping in unsupervised way to get more and more data to that. And then you are using your machine learning algorithm for prediction algorithm for that purpose. The second area is there is huge amount of the knowledge base buried in the data which nobody looks, or humans are, because human-machine interaction, I will say that human-machine interaction, if there is any failure happens or any fault happens, then field engineers will go to that and they will troubleshoot. If you read those things, you will learn hell amount of the things from that data set, because these people have experience of 20 years, 30 years, basically, who are resolving these kind of the issues. So how to capture the domain knowledge from that data set? That's another area, and convert that unstructured data to structured data. Now you are getting a lot of contextual information. Now you can build your causal network, so because you need that data. So I think machine learning community can help immensely by generating the data and bringing that data. Like Facebook, what they do, they see your picture on, and then they will send that picture to you. You are tagged on that. If you liked it and you tagged, they get the feedback immediately. And then their algorithm will become much smarter. So think in the same way, like for the industry, I think we can do tons of the things on that also.
Thank you. Any other questions from the audience?
You did mention that the autopilot is far superior to the pilot in bad weather, right? What stage does a closed loop control system become too complex for that trust to be
So first of all, that I'm not working on that problem. I took it as the example from that public book, and once again, Boeing as well as other. So in safety, I haven't used machine learning, for safety critical systems. I think I used it more as an example of making systems. So was of an example of making the system humans plus the intelligent machine learning predictor or whatever you have. If we try to optimize the right function, which is typically not a class or a probability or a conditional probability or some continuous value, but something more complex and higher dimensional, I think that if we train it as, we know how to train things right now and to minimize all sorts of functions, right? I think we can, just to address the global optima, right? The global optima is to have the system fly very safe. I think we can do it. And now, for that, again, there are simulations. And in that area, so for example, the X-plane simulator, which you all can buy, for certain tasks, is certified by the FAA. So if you're from the academia and if you have an idea of, I think I can do this thing better in decision in flying, you can buy the simulator and prove it. And so the simulator is certified by the FAA. And if you do it better than what's in practice, here's your solution. So, and you have these kind of things that are available, to the outside world.
So we're kind of coming to the close of the hour, and I want to make sure everybody has time to go to the general opening. So I just had one last question, maybe for all three of you, and we heard a little bit on that and different questions or answers, is that don't just stop at the prediction or the ROC curve. Look at what happens next, and also what domain knowledge can bring in to PHM, particularly when we are looking at machine learning. So where do you think is the boundary for machine learning, or is there is machine learning the silver bullet everybody is talking about and you can use that towards PHM tasks, or there are certain things for which you have to bring in the information from the other side, from the physics and the understanding of how you build this system? Because we are not talking about humans, right? We are talking about systems that were designed and built by us. So where is the boundary? What it is that machine learning can bring to the table, what it cannot? So if you can talk about that.
Sure. So I'm trying to think of what it can't bring to the table. I'll go to the other side. I mean, the real where we are at this point, the main benefit, all of the work that we're doing, at least at United Technologies, is focused around the area of multimodal sensor or information fusion, right? So we see the real value of these technologies as really for the first time being able to make use of the system data. I mean, you'd be surprised how much of the PHM is still done on single or 2, 3 sensors at a time. So we're able to now model implicitly much more of the contextual information of these systems, where in some sense, for these when these models are trained well, they're picking up some of the the transfer functions, the coupling of these systems. For anyone who's tried to model complex systems with many components, you know that you can't just stick them together into one large simulation, right? These things error propagation is simply too much when you're trying to combine them manually. And so I see that as the main input. Obviously, we're modeling physical systems, so I mean, we are generating physics information. There's no reason, as I mentioned earlier, not to put it in explicitly. And of course, information is information. Whether it comes from the data or the domain experts, you should make use of all of it and try to figure out how to do that.
Thank you.
The short answer is yes. Machine learning and AI can address this serious problem. However, I'd like us to think more about, so right now we have, just in supervised learning, we have these two extremes. Either we throw in a large feature space to a deep learner, or we build features that have in themselves some systems information built from a domain expert. So for supervised learning, I'd like us to think that probably the optimal is somewhere in between or in a hierarchical solution. Beyond that, as an intelligent system, we should think about sequential decisions and the multiple decisions and not only point decisions the way we do in supervised learning. Our decision has a consequence, it's acted upon. We don't care about that right now in supervised learning, and we'd like to care about that, so we have to think about other frameworks. And for outside sciences, outside of AI and machine learning, I'd like to see simulation and formal methods for validating what we produce as part of the system. I think that can provide pretty good solution for complex systems like the ones we talked about today, and like the ones we care about.
Thank you.
Yeah, so I think so far we have been using machine learning to build models, but model in itself is nothing. Like, unless these models are taking some actionable, making some actionable decision, basically. So yeah, how to combine output of machine learning to the downstream systems, like if suppose you detected some anomaly, and if you can do the disruption management for airlines, then definitely you can do. So yeah, you have to stitch machine learning output so that you can do some simulation at the top of that. You can fly forward those models to the future and do the scenario analysis on that, and then apply some optimization algorithm or simulation algorithm to achieve some business outcome. So I think that's the marriage which we need to have between multiple disciplines. Like, you can use machine learning and maybe AI for the path planning or those kind of the problems people have solved or solving. So it will be the combination of, I will say, machine learning plus many other analytics disciplines at the top of that. Even whenever we are building these models, like just pure machine learning models will not be sufficient. You need to do a lot of signal processing on the data set. So traditionally in the PHM community, signal processing people or controls community has built a lot of solutions. So now how to marry with the machine learning and then at the top of with the optimization, I think that's the direction at least we are taking right now.
Thank you. Any last questions from the audience?
I wanted to raise one more point, which
Yes.
is beyond this. I'm part of a big company, Boeing, and recently we had to deal a lot. So we have people in our company and executives who are not familiar with machine learning. They read about so right now in front of many people is put a very big hype that we have solutions for pretty much everything. And I think IBM Watson is one big reason, the way they, no, frankly, sorry. And it's not the IBM TJ Watson group, but it's the PR, and look at. We should be aware of that. You heard as part of this panel and as part of this workshop how many open research questions we have and how hard it is for us to produce a solution that's usable and that's accurate and that's trusted and so on. I'd like you all to, this hype can damage the funding available for our efforts and the and the seriousness of this community and the machine learning community and the AI community. We should all stand towards that, because I can tell you there are executives in my company who believe that, our group is too slow because I'm not doing, what Watson says on TV, that they're solving all the problems. And it's a danger. It's a danger for, big companies where you have these executives thinking that machine learning has solved everything. So you've seen here, there are many open research questions. Let's go and address them at home. And let's fight against this big hype. It's big, and it may damage us in the future. So,
Agree. Thank you. So let's thank our panelists. We have a few announcements before we disband.
All right. So we won't take too long. First of all, I want to thank everyone, all of you for coming, our panelists, our invited speaker, and of course the workshop wouldn't be possible without all the hard work from the program committee. So I'm not going to list out all the names, but some of you are here. Thank you so much. And I want to announce the winner of the Best Student Paper Award. I'll give it to Michael. UTRC is sponsoring an award. So first of all, you saw the presentation earlier. I'd just like to say we're happy to present the Best Student Paper Award to Nirali Virani and Devesh Jha from Penn State on their paper of sequential hypothesis tests using Markov models of time series data.